Hi everyone, this is Merlin calling from the Netherlands with a very quick and dirty video regarding the following question. Minus 20 dB plus 2 dB equals how much? This question originated on Nathan Lively's Facebook page called Sound Design Live, a fellow instructor, where somebody asked, has anyone worked out a quick way of summing dB values? Minus 20 dB plus 2 dB, for example. And this is the thing, even though we work with decibels on a daily basis, I feel it's safe to say that our understanding of the decibel is poor. It's not intuitive. It's abstract. It involves a logarithmic scale, and adding and subtracting decibels is not as straightforward, for example, as adding or subtracting on a linear scale like a ruler or a tape measure. And yet we work with the dB for most of our careers on a daily basis. So it would be kind of in our interest to have a thorough understanding of this decibel. Imagine that you have a nurse that is in charge of sedating you for surgery, and she doesn't have an understanding of what a milliliter is. Well, that could become very problematic. If she gives you too little sedative, you will be in a lot of pain during surgery. And if she gives you too much sedative, then you might never wake up, even if the surgery was successful or not. So just like we all realize that it's important for a nurse to understand a milliliter, you could claim that it's, well, equally important for a sound engineer to have a thorough understanding of a decibel. So what if we want to answer this question? Minus 20 decibels, a negative value, plus 2 decibels, a positive value, equals how much? What if we want to do this the formal way, using all those fairly complicated, but certainly not rocket science, but fairly complicated equations? Well, most of you will have heard that there are two equations. There's the so-called 20 log rule, and there's the so-called 10 log rule. Well, I will not elaborate on the 10 log rule, which we only use for power. I will solve this problem according to the 20 log rule, which is what we use most of the time when we're dealing with, in this instance, for example, with pressure or voltage. Because the decibel is a ratio expressed on a logarithmic scale. Now, ratio or fraction is, or percentage is three ways of saying the same thing. So it is a fraction expressed on a logarithmic scale, or it could be a ratio expressed on a logarithmic scale, or it could be a percentage expressed on a logarithmic scale. And this is basically three ways of saying the same thing. So let's look at the formal equation first. There we go. There you have it. The decibel equals 20 times log base 10 of a fraction. And there you see your ratio, your fraction or your percentage. It's the part between parentheses. Level 2 with respect to level 1. That is a fraction. Now notice I said log base 10, which is the red 10 that you see in subscript behind the word log. Normally you don't see this in writing because it's implied. Unless the base number is specified specifically, we always assume that we're dealing with base 10, and that is so common, it's so implied that nobody goes out of their way of writing base 10. But for the sake of simplicity, I've put it in here anyway to make sure that we all will end up pressing the right buttons. So it says decibel equals 20 times the log base 10 of a fraction level 2 with respect to level 1. Well, we want to add minus 20 dB and plus 2 dB, which means that we need to go from the logarithmic scale, which is what a decibel is, to which fraction belongs to those particular values of minus 20 and plus 2 dB, which means that we need to rearrange this equation so that we can go back from a certain decibel value to the fraction that was responsible for that particular value. So if we rearrange our equation, this is what we want to know, the fraction. If we rearrange our equation, then level 2 with respect to level 1, there's our fraction, equals 10 to the power of our decibel value divided by 20. So if I want to know ultimately what level 2 is, which is my goal, then level 2 is equal to level 1 times 10 to the power of our decibel value divided by 20. Now, we can make life very easy, very simple by setting level 1 simply to a value of 1, which we are free to do. So if we substitute all the green level 1s by green 1s, then things become much, much more easy. Okay, level 2 equals 1 times 10 to the power of our decibel value divided by 20, which means that we can forget of the 1 altogether for now. And let's remove the 1 out of the picture altogether, and then you simply see that on a linear scale, the level for a certain decibel value is simply 10 to the power of that particular decibel value divided by 20. So there you have the formal rule. This is what we call the 20 log rule, which we apply for pressure and voltage. Not to be mistaken for power, for which we have a 10 log rule. This is the rule that we will use to solve this problem in a formal way, which means that we first need to figure out what is the fraction that belongs to minus 20 decibels and what is the fraction that belongs to plus 2 decibels, because we cannot simply add and subtract on a logarithmic scale, unlike a linear scale, a ruler or a tape measure, for example. So let's bring up a whiteboard and let's figure out, okay, according to the 20 log rule, which says that 20 times log base 10 of a certain fraction, L2 divided by L1, okay, we want to know the fraction that goes with that particular decibel value. So we rearrange the equation and we say, okay, our fraction L2 divided by L1 is 10 to the power of that decibel value divided by 20. And since we made life easy by setting L1 to 1, it basically disappears altogether, and that brings us to level equals 10 to the power of our decibel value divided by 20. And this we want to figure out for minus 20 and plus 2 first. So if I want to know, if I have a minus 20 decibel value on a logarithmic scale and I want to go to the linear scale, then I need to know which fraction belongs with that minus 20 as well as which fraction belongs to that plus 2. So let's do minus 20 first according to our formal rule, which you see over here. So I'm going to bring up a calculator and you see the equation in the bottom right corner. We know our decibel value, so we start with 20 decibels negative. This is what we want to know on a linear scale. Divided by 20 gives us minus 1. So the question becomes, what is 10 to the power of minus 1? So there we go. 10 to the power of negative 1. Oops, sorry, typo. 10 to the power of negative 1 equals 1/10. So there you go. Minus 20 decibels expressed as a fraction, as a ratio, or as a percentage equals 1/10. So let's bring back the whiteboard and we're going to say, okay, this is the same as 1/10 or 0.1, which is of course 1/10. That is the fraction that represents a value of minus 20 dB on a logarithmic scale. Now we have to do the same for our plus 2 value. So let's reset our calculator. What is 2 decibels divided over 20? Well, that is 0.1. So we are looking for a value that is equal to 10 to the power of 0.1. So here we go. 10 to the power of 0.1 equals, oops, typo again, 10 to the power of 0.1 equals 1.2589, so on and so forth. So why don't we note this number in our whiteboard, and let's call it 1.26. So on a linear scale, the plus 2 value becomes 1.26. Now on a linear scale, I can add and subtract, which means that I can now add my 1/10 to my 1.26, and that becomes 1.36. That is our sum on a linear scale. And the question becomes, how much is this expressed in decibels? We have to go back from the linear scale to the logarithmic scale. So let's go back to our calculator. There's our calculator. 1.26 is plus 2 decibels expressed on a linear scale. And now I want to add the 0.1, which we already figured out, which is our minus 20 decibels on a linear scale, which makes this 1.36 as we saw on the whiteboard. This is now my ratio. This I want to express in decibels. So now we have to go back from the ratio to the decibels, which means I press my log, base 10. You see, calculate the base 10 logarithm of the displayed value. I now press this button and multiply the outcome by 20, which gives us 2.66 dB, which is what we saw in the forum post, in the Facebook post on Nathan Lively's page. This is the formal way with a very high degree of accuracy because there's only about 16 or so decimals, values behind the decimals. So this is the scientific way, if you will, of calculating minus 20 dB plus 2 dB using a calculator. So if we bring up the whiteboard, we can say that on a logarithmic scale, it becomes 2.66 dB, which is a very small increment if you look at the values. If you add minus 20 dB, okay, and you add plus 2 dB together, the total value, the sum, only goes up by 2/3 of a decibels, which is almost negligible if you think about it, because 1 dB on average is the smallest audible step anyway. So this is the outcome according to the formal way using a calculator, which is a cumbersome process. It's not rocket science, it's a cumbersome process, and it remains to be seen, is this degree of accuracy for live sound reinforcement, is this degree of accuracy called for, or can we do a reasonable guesstimate and still feel comfortable about the outcome? That is the thing that I would like to discuss now from here on, because minus 20 dB plus 2 dB, what is much more important to me, and this is what I work at in my seminars, is to grow a sense of intuition, to grow a sixth sense, if you will, for decibels. Because just by looking at these values, I could also argue, hang on, minus 20 dB and 2 dB are values that are separated by over 20 decibels. If I draw a line and, okay, we call this 0 dB and we call this minus 20 dB, and we have over here to the right, we have plus 2 dB, and we look at those values, then these values, on this line from left to right are almost separated. Well, they are separated by 22 decibels. And that means that you could also say, hang on, these values are isolated from each other. Okay? What do we mean by isolation? Well, the negative 20 decibel value is too soft to have any tangible effect on the plus 2 dB value. It's too soft to matter. It's too soft to make a tangible, profound change if we add these two values together. And that is, of course, a much more interesting analysis before we start calculating this with great accuracy using a calculator, that you have an intuition, a sixth sense that says, hang on, these values are separated way too much for the minus 20 dB to have a tangible contribution, a tangible effect on the plus 2 dB, because there's isolation. And maybe you have never heard of isolation until now, in which case I strongly encourage you, this is what we're talking about. We're talking about Bob McCarthy's summation zones, which is the decoder ring. This is the most important thing that I try to teach during my seminars. This is the essence. This is where I say this is the menu or the recipe or the formula. If you can digest this system, you will be able to instantaneously determine that these values, minus 20 dB and plus 2 dB, are separated way too much to have any meaningful outcome. Now, there's no time, and it's also outside the scope of this video, to explain in great detail what the summation zones, what Bob McCarthy's summation zones are all about. But for those that own a copy of his book, okay, read up on the chapter summation. Okay, this is where this explained in great detail. So if you own a copy of Bob McCarthy's Sound System Design and Optimization, go to the chapter summation, which would start on page 60 in the first edition, chapter 2. In the second edition, it would be also chapter 2, starting on page 61. And for those that own a copy of the third edition, it is chapter 4, starting on page 125. And then you will be able to appreciate that these numbers are separated too much to have a meaningful, tangible outcome. So let's see if you and I can reason why this is. In my seminars, there's the so-called five-fingered rule. Some people have come to call it the five-fingered rule. This is not a name that I came up with, but I encourage my students to memorize 5 key ratios according to the 20-log rule. And where I claim if you can memorize these 5 ratios, these fractions, then you will be able to calculate decibels on the back of an envelope without ever having to resort to a calculator again. And this is the only way that I can think of that you can grow an intuition for decibels without, without being a rocket scientist, which is not the goal of what we're doing here. So let's look at these 5 ratios. A ratio of 1 on 1 is 0 dB. I mean, if I give you 2 identical batteries with equal voltages, 2 clones of the same batteries, then there's no difference between those batteries. So a ratio of 1 over 1 is equal to 0 dB difference. There's 0 dB difference between 2 identical 9-volt batteries. However, by the time we have a ratio of the square root of 2 over 1, then we talk about a 3 dB increase, and when we have the inverse, if we have 1 over the square root of 2, we talk about a 3 dB reduction. And you have to take my word on this. A 2 over 1 ratio, according to that 20-log rule, is an increase of 6 dB, whereas the inverse, a 1 over 2 ratio, is a reduction of minus 6 dB. Again, you'll have to take my word for this. 3 over 1 is very close, not all the way, but very close, is approximately plus 10 decibels, whereas the inverse, 1 over 3, is approximately minus 10 decibels, and ultimately a ratio or a fraction of 10 over 1 is a 20 dB increase, whereas 1 over 10 is a minus 20 dB reduction. And there's another rule of thumb which is very easy. Whenever you multiply by 10, which we're doing with a 10 over 1 ratio, or divide by 10, which we're doing with a 1 over 10 ratio, whenever you multiply or divide by 10, the answer resides in the name of the rule that you use. And since we're using the so-called 20-log rule, the name of the rule suggests that if you multiply by 10 or divide by 10, you either gain or lose 20 decibels. And if you can memorize these 5 key ratios, the 5-finger rule, then you can calculate decibels on the back of an envelope. And let's see, by applying this system, how far you and I can get, assuming that we can memorize these values. So let's start making a list together. Let's start making a list, and let's see if we can do 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, 6 over 1, 7 over 1, 8 over 1, 9 over 1, and ultimately 10 over 1, and see if you and I can come up with the decibel values that correspond with these ratios, or fractions, if you will. Well, 1 over 1, that means there is no difference. You have 2 identical batteries. They don't differ from each other in any way, so that's going to be a 0 dB difference. 2 over 1, according to that 5-fingered rule, is a 6 dB increase, which leaves us with 3 over 1, which according to the same 5-fingered rule would be a 10 dB increase. Now we get to 4 over 1. Well, 4 over 1 is not a member of the big 5. So how can you and I calculate 4 over 1 and be confident about the outcome? Well, here we go. 4 over 1 is not something that I've memorized. It's not a member of the big 5, but I can decompose 4 over 1 into smaller fractions, of which I do know my decibel values. And convince yourself first that this is true, otherwise there's no point in continuing this video. However, according to that five-fingered rule, 2 over 1 is an increase of plus 6 decibels, which we've done twice. So that becomes plus 6 and plus 6. That becomes plus 12 decibels in total. So with a little massaging, I actually do know 4 over 1, provided I decompose it into smaller chunks of which I know the corresponding decibel values. So I can continue my list and say this is very much plus 12 decibels, which brings us to 5 over 1. Again, 5 over 1 is not something that I've memorized by heart. However, the question remains, can I somehow write 5 over 1 in another way that leaves me with fractions of which I know the corresponding decibel values? Well, maybe if we double up, if we basically double numerator and denominator by 2, then it leaves us with 10 over 2, which is exactly the same as 5 over 1. However, 10 over 2 can be written as 10 over 1 times 1 over 2. And those two fractions are very much members of the five-fingered rule, which means that now I'm in business. I've memorized my five-fingered rule, which states that if you multiply by 10, the answer resides in the name of the rule that you use. So 10 times more is an increase of 20 decibels according to the name of the 20 log rule. However, 2 times less is a 6 dB reduction. And if I add plus 20 and minus 6 dB, that leaves me with plus 14 decibels. So I do know 5 over 1, but it takes a little bit of massaging. So let's continue our list. That is going to be a 14 dB increase. So let's go to the second column and continue with 6 over 1. 6 over 1 is not something that I memorized, but maybe I can decompose the 6 over 1 into something smaller, of which I do know the corresponding decibel values. Let's say 2 over 1 times 3 over 1, and convince yourself first that this is true, otherwise there's no point in continuing this video. However, these fractions are members of the five-fingered rule, and I know that if I have a 2 over 1 ratio, that is a 6 dB increase, and that if I have a 3 over 1 ratio, that's a 10 dB increase, according to my five-fingered rule, saying me that 6 and 10 together becomes a 16 dB increase. So I do know 6 over 1 and can continue my list. That is a 16 dB increase, which brings us to 7 over 1. Again, 7 over 1 is not something that I know by heart. So is there a way that I can turn 7 over 1 into something that I actually do know? Well, again, maybe the answer is simply doubling up. What if I multiply the numerator upstairs and the denominator downstairs by 2? It leaves me with 14 over 2, which I can also write as 10 over 1 times the square root of 2 over 1 times 1 over 2. Now, you might say, hello, where does the square root of 2 come from? Well, I would like to remind you that the square root of 2 is approximately 1.4. So if I put in parentheses here 1.4, then hopefully you'll come to the conclusion that the three terms on the right-hand side is exactly the same or very close to 7 over 1, with the exception that I do know all the corresponding decibel values that go with these fractions. Because if you multiply by 10, that is a 20 dB increase. But if you multiply only by the square root of 2, that is a 3 dB increase. However, if you divide by 2, that is a 6 dB reduction. And now I can add and subtract, and you will see that 20 plus 3 decibels equals 23 decibels, plus minus 6 leaves me with plus 17 decibels in total. So I do know 7 over 1, which is 17 decibels, which leaves me with 8 over 1. 8 over 1 is again not a member of the five-fingered rule, but maybe I can decompose my 8 over 1 in, let's say, 2 over 1 times 2 over 1 times 2 over 1. And I call this the longhand notation, because normally I would say, hang on, this is 2 to the power of 3 over 1, which would be my shorthand notation. Now, the convenient thing of the shorthand notation is that I instantaneously see that I doubled 3 times, and for every doubling, I gain 6 decibels, making this 18 decibels. I could also have done it step by step, because I know that if I double, I gain 6 dB, which we have done 3 times, and that would confirm the same 18 dB increment. So there's several ways how I can write this. More important, I do know that an 8/1 ratio is an 18 dB increase, which leaves me with 9/1. Again, 9/1 is clearly not a member of the Big Ten, but maybe I can decompose 9/1 into something smaller, of which I do know the corresponding decibel values, like 3/1 times 3/1. That would be the longhand notation, or 3 to the power of 2 divided over 1, which would be the shorthand notation. I have memorized my 5-finger rule, and I know that a 3/1 ratio is a 10 dB increase, which I've done twice, and that would suggest a 20 dB increase, or if you want to write it all out, plus 10 equals plus 20. In other words, my 9/1 equals plus 20 decibels. Okay, well, promising. Which brings us to 10/1. 10/1 I already knew. It's an actual member of the 5-fingered rule. And if you multiply by 10, then the level goes up by 20 decibels. Oops! And now we're presented with a challenge, because now I have 2 instances of plus 20 decibels. Surely this is an inequality. Surely this can't be. One of us is cheating, which is probably me. Which of these plus 20 decibels is the real winner, and which one is the approximation? Well, I know for a fact that 10/1 is exactly 20 decibels, which means that I've cheated with 9/1. But now comes the beauty of it. Let's look at the pattern. Let's look at that second column. If a 6/1 ratio is 16 decibels, and a 7/1 ratio is 17 decibels, and an 8/1 ratio is 18 decibels, then what would you expect is a 9/1 ratio? I mean, 10/1 is 20 decibels. 8/1 is 18 decibels. If you say that 9/1 is 19 decibels, then I feel confident that you cannot be off by more than 1 dB, which happens to be the case. So, this all pops out quite conveniently, and these are progressions that with a little effort are not that hard to memorize. However, if 9/1 is 19 decibels, then 3/1 cannot be 10 decibels, which it isn't. So I need to correct this and split hairs and say, well, then this is strictly speaking 9.5 decibels. But I've said from the beginning, 3/1 is conveniently close to 10 decibels. It also means that my 6/1, which was 2 times 3, if you remember, cannot be 16 decibel, which it isn't. It is, to be exactly more precise, it is 15.5 decibels. But now I'm really starting to split hairs. And all of this could be done on the back of an envelope, provided that you memorize your 5-fingered rule. Okay, so back to the original question. If I add minus 20 and 2 decibels, why is that minus 20 dB too soft to matter? Why will there be isolation? Why will have minus 20 dB will have no tangible effect on the plus 2 dB? Because it's simply way too far removed from the plus 2 dB. Well, let's see if you and I can do this on the back of an envelope. We already said, okay, if I draw a line, and okay, we put 0 to the right and plus 2 slightly more to the right and minus 20 to the left, then you can already see that these guys are separated by 22 decibels. That is a huge gap, if you will. That minus 20 dB is going to be too soft to matter. And we want to add these figures together. Well, let me suggest that we do an intermediate step. Instead of adding minus 20 and plus 2 together, let's start with a slightly smaller step and simply add minus 20 and 0 together for starters. Well, the first thing that we need to know, since these are decibels, this is on a logarithmic scale, we need to know what are the linear values that go with those decibel values. Well, minus 20 is 1/10, and 0 on a linear scale becomes a 1. So if we want to add minus 20 dB and 0 dB, then we're adding 1/10 and 1 on a linear scale. So let's put that in a slightly more better organized overview. Minus 20 and 0, what does the outcome become when we add these together? Well, I already said it, minus 20 is 1/10, 0 is 1, and on a linear scale, I can very much add and subtract. On a linear scale, yes. And then it's very apparent that 1 and 1/10 becomes 1.1 in total. Now, 1.1 expressed as a percentage would be 110%, which means, in other words, that the level would have gone up by 10% when we add minus 20 dB and 0 together. A 10% increment. Now, if you take out your calculator, you will see that 10% is approximately 1 dB, slightly less. So here you see it. If I add minus 20 dB and 0 dB, the level only goes up by a very small amount, only goes up by 1 dB, which is the smallest audible step on average, which is not much if you think about it. I could also do subtraction, okay? And it's outside the scope of this video, but suppose that of one of these two signals, the polarity would be inverted. Let's say that this signal would be polarity inverted. So not in phase, but out of phase. Well, the only thing that changes is that addition becomes subtraction. And now we subtract 1/10 from 1, leaving us with 0.9 if we add these two values together. 0.9. And that, as expressed as a percentage, would be 90%, which would be 10% less at the end of the day, which would make the total sum minus 1 dB. No longer plus 1 dB, but minus 1 dB, because the moment you flip the polarity, addition became subtraction. And we ended up subtracting 1/10 from 1 instead of adding 1/10 to 1. And that is exactly what you will see in the bottom row of Bob McCarthy's summation zones. If you look at the bottom row and you see that there's a 20 dB level offset, you gain 1 dB at most and you lose 1 dB at most. Because with a 20 dB level offset, you are isolated. And regardless whether that signal is in phase or out phase, it is too soft to matter when you add two signals together, which are separated by 20 dB, which have a level offset of 20 decibels. Regardless whether it's in phase or out phase, it is too soft to make a dramatic change. And that is, of course, the much more important implication, that if we look at these values, that we say, hang on, regardless whether this value is in phase or whether this value is out phase, it is too soft to make a difference, a tangible difference, which is what is much more meaningful to me when we talk about designing systems and calibrating systems. So let's finish this video up and say, okay, we already know, from the previous example, we already know that if we add minus 20 and 0 decibels together, if we add these together, that is going to be a plus minus 1 dB difference, okay? But the original question started with, what if we add minus 20 and 2 dB together? Not minus 20 and 0, but minus 20 and 2 dB. Okay. which means that, I'm no longer interested in the 0. Now we want to know what happens if I add minus 20 decibels and 2 dB together. Well, those values are separated even further. But the question becomes, what is plus 2 dB expressed as a fraction? Okay, well, maybe I can extract that from the table that I made. Notice that over here we have two values that I'm singling out. A 4/1 ratio is a 12 dB increment, whereas a 5/1 ratio is a 14 dB increment. And the relative difference between 12 and 14 decibels is the 2 dB that I'm looking for. This is the guy that I'm looking for, which means that, in other words, I can also express a 2 dB increment as a 5/4 ratio, because 5/1 is a 14 dB increase, whereas 1/4 is a 12 dB reduction. And if I add those guys together, that will leave me with a 2 dB increase. So I do know the fraction. It takes some massaging, but I do know the fraction that belongs with 5/4, or the fraction 5/4 belongs with the plus 2 dB, which means that I can go back to the original problem, which stated what is minus 20 decibels and 2 decibels, now that I know that 2 decibels expressed on a linear scale is 5/4. This is the problem. This is what I want to know. And that means that I figure it out. On a logarithmic scale, I want to add minus 20 and I want to add plus 2. However, on a linear scale, these decibel values are represented by 1/10 and they are represented by 5/4. And on a linear scale, I can very much add and subtract. And that means that I want to know what happens if I add 1/10 and 5/4. Well, at this point, that is apples and oranges. I cannot add 5/4 and 1/10 together because the denominators are not the same. So let's fix that by saying you're trying to add 50/40 to 4/40. And now I am in business. And the outcome will be, of course, 54/40. And, I can stop here because my intuition is already telling me that the 4 value that I have over here, in comparison to the 50 value that I over here have on the left hand side, that is less than 10%. And that means that the level increase will be less than 1 dB. If I add less than 10% to the value that I started with, the level will only go up by less than a decibel. We already knew that, if you add 20, minus 20 and 0, that the level will go up by as much as 1 dB, let alone if you add minus 20 and plus 2, which are separated even more further apart, 20 decibels apart, then the level increase will be actually less than 10%. And I think it's safe to say that if we look at the original outcome, where we said, okay, using the calculator, adding minus 20 and plus 2, and notice that this value is very close to 5/4. Notice that if we add these two values together, then at the end of the day, our plus 2 goes up with less than a dB. Okay? So if I had to err on the side of caution, I would say, well, it will be 3 decibels at most, if not less, because the minus 20 decibels contributes less than 10% to the plus 2 decibels. And that is the intuition, that is the sixth sense that I wish for everyone that is working with decibels on a daily basis. And again, okay, This entire analysis assumes, of course, that you have memorized your five-fingered rule. That is, of course, the underlying system. But if you memorize these values by heart, these key ratios, you will be able to instantaneously say, okay, whatever the outcome will be, that minus 20 decibels is isolated of the plus 2 decibels, and it will make no or little difference because whatever it adds is less than 10%, and if it's less than 10%, the level will not go up by more than 1 dB. So what if we have two values, just to finish it off, what if we have two values that are not isolated from each other, two values that are actually closer to each other? What if I want to add, let's say, 94 decibels on a logarithmic scale, and I want to add 100 decibels on a logarithmic scale? These values are only separated by 6 dB. There's no isolation. Can I still use my five-fingered rule to add these values together and calculate the outcome? And the answer is yes, but you have to go from the logarithmic representation from the decibel value. You have to go to the linear value where everything is expressed as a ratio, which you can actually add as a fraction, or percentage, which you can actually add. And I'm going to aid myself in the process to arbitrarily, okay, this is the first thing that comes up, I'm going to subtract 94 dB, okay, from both values, which leaves me with a 0 over here, and it leaves me with a plus 6 over here. And you might say, well, why does he do that? Because now I'm in business. I know that 0 decibels on a linear scale becomes a 1, and plus 6 decibels on a linear scale becomes a 2. And now I'm in business because those are values according to the five-fingered rule. If I add 1 and 2 together on a linear scale, I'm left with a 3. And I know that a 3 is approximately a 10 dB increase, but if we split hairs, it's going to be a 9.5 dB increase, that 3. The only thing that I need to do is to add the 94 dB that I subtracted before. I need to add that again, and then you will see that this becomes 103.5 decibels. Okay, and this is perfectly sound, okay, for adding two values, two pressures that are in phase. Of course, that is important to mention if we're talking about addition, because if you flip the polarity, addition becomes subtraction. So, knowing the five-fingered rule is a very powerful set of rule of thumbs that allow you to calculate decibels on the back of an envelope and be accurate within 1 dB or less. And this is what I wish, for the people, among others, but this is what I wish for people that attend my classes, that they get a sixth sense, a intuition for decibels, so that they can do operations like these, or look at this particular one and see at first sight that this is not going to be a tremendous increment because these values are separated too much. Do I use a calculator in the field? Sure. I use a calculator in the field, and it gives me more accuracy. Am I dependent on the calculator? No, I'm not. And more important, I will have a sixth sense that instantaneously informed me that whatever value, every number appears in the display of my calculator, I will have a sixth sense telling me, a spider sense telling me, hang on, that value is too large or too small, or there's something wrong. I must have pressed the wrong buttons. And that is the end of this very quick and dirty video, and I hope it does for you what it's been doing for me. Okay, enjoy the rest of your day and speak to you soon.